Okay, welcome to guide sheet number 5, the last of our guide sheets for work and energy topics. In this one, we're just going to look at the way you can use different methods to help you track the energy in a moving system, specifically bar charts, like using a bar graph. Really, energy is a lot like a counting process. You're similar to a checking account. Money comes in, money goes out. You're keeping track of the total to see how much you have. With energy, we can transfer between different accounts, potential, kinetic. We can have potential energy from gravity, potential energy from springs in terms of mechanical systems. And we can also take energy out or put energy in by doing work. If work is negative, we're taking energy away from the system. If work is positive, we're adding energy to the system. Now, a good example of the bar charts can be seen in this little simulation that runs over and over again from the physicsclassroom.com. It's tracking the kinetic energy, the potential energy, and the TME, or total mechanical energy, of a roller coaster as it goes up and down hills and through loops. Now, because the potential energy is gravitational potential energy, the pathway has nothing to do with the energy at any point in time. Gravitational potential energy, an internal force, is path independent. It's just measured based on the mass, the height above some zero level, and then the acceleration due to gravity. Here locally on the Earth, 9.8 newtons per kilogram, or around 10 newtons per kilogram. Now, as you watch this thing going around the loop, as it's higher, it's going to have more potential energy. The potential energy line, the zero line, is right there where it ends. So it's maximum potential starting from rest. It's converting that into the kinetic energy that's speeding it up. Now, as it goes up the loop, to pay for getting up the loop, it has to slow down. It has to give away kinetic energy. In the next loop, it doesn't go as high, so it doesn't lose as much kinetic energy. And the word lose is a risky one because it's not actually losing the energy. It's just being transferred between types, kinetic to potential, potential to kinetic. In this case, we're making some big assumptions that no air resistance, no friction, no external forces are acting on the roller coaster. I can tell that because the total mechanical energy stays constant. So we're changing between the forms, potential and kinetic, but the total stays the same. So in our guide sheet here, what we're doing is looking at some different situations, and we're just going to sketch our own little bar charts based on what's happening. This would be a really good thing, chance to use highlighters or different colors to help you out as you're going along. I like to use different colors for each one. I'm going to use green for kinetic because the kinetic energy is the energy of motion. You should be moving, going when that happens. I'm going to use this reddish color for potential, and then I'm going to go ahead and use yellow for work. Now, those are the colors I happen to have. Again, you can pick any colors you wanted. Okay, so we look at our situation. A ball falls from the top of the pillar to the ground below. The initial state is at rest at the top of the pillar, and the final state is just prior to striking the ground. So everything to the left of the equal sign is our initial energy state, plus any work that's done in the motion. So this will be from the top down to the bottom. The final energy on the right-hand side is just before we hit the ground. Again, it's not after we hit the ground, because then we're going to transfer that kinetic energy into other forms of energy, sound, compression, all kinds of different things going on. Now, the object starts from rest, so there will be no kinetic energy to start with. In order to have kinetic energy, you have to be moving. So the kinetic energy bar would be at 0. The object is at its maximum height at the beginning, so it has maximum kinetic energy. Now, there are no numbers in this, so I can pick any amount I want. I'm just going to pick 4 as an arbitrary choice. So 4 boxes of potential energy. Now, that's positive potential energy. It's above 0, so it now has the ability to fall. Now, In this one, the ball falls from the top. The initial states, it says to ignore air resistance. That means we're going to ignore friction. We're going to ignore those external forces. Since gravity is the only force doing work on the ball, the work arrow would also be, the work bar chart would also be at 0. There's no work being done because there are no external forces being done. So in terms of this equation, we can cross off the external work. We're at rest, so we don't have any kinetic energy to start with either. So no work because there are no external forces. No kinetic energy to start with because we're at rest. Now at the end, we're just about the ground, so our potential energy would have also gone to 0. Now the energy can't just have disappeared, it had to turn into something. So in this case, it would have turned into kinetic energy. And if I had 4 positive bars to start with, I will have 4 positive bars to finish with. So this is a straight up energy conversion. The potential energy at the beginning is going to be equal to the kinetic energy at the end. Height equals, we're assuming the height is 0. It's just before it hits the ground, but that's what we're going to call that our 0 energy level. Okay, we'll try one more and then we'll split the tape and go for another take. So now this is a little different. Instead of just falling, we're moving a car. Car skids from a high speed to a stop with brakes applied. The force of friction does the work on the car, thus changing the total mechanical energy. Again, key elements here is that we are moving to start with, and then our velocity is 0 at the end. So over here at the final, there'll be no kinetic energy. It'll be 0. The potential energy is based on whatever we call 0. So if I say this is height equals 0, then I don't have any potential energy in either case. So what I have is a certain amount of initial kinetic energy, and I'm just going to arbitrarily pick 5. Now, we have to get to a state of no mechanical energy. We have to be stopped on this 0 height. So that means that we have to get rid of that kinetic energy somehow. Now, we didn't have any potential. Now, we could have picked the height as not 0, and we could have had some potential, but it would have stayed constant through between both places because the level of the ground is level. We're stopped, so we have them there, and we're again at the same height, so we have nothing there. So the kinetic energy is going to have to, plus the external work done, is going to have to add up to 0. Now that means that we're going to have to take energy away from the system, and we're going to have to take away as much as we had. So since I had 5 positive bars of kinetic energy, I'm going to need to take away 5 negative bars of work. And that work is being done by friction, which is a force external to the system. It's going to convert the kinetic energy into thermal energy, thus taking it away from the mechanical system. Okay, so that's this episode. We'll wrap it up in episode number 2. Hopefully you get a chance to see that soon.